Oh. Hi, Ellie, good morning. Maybe I should rename our class Total Chaos instead of Total Physics due to events in the US. Let's hope the chaos has an end rather soon. Okay, anybody else there? We got Ellie, we got anyone else? I see a couple people. Yeah, okay. Good morning, whoever you are. That would be Zach. Good morning, Zach. So we need Anne-Sophie and Teresa. Then we'll be complete. Let's review some stuff here. I don't know if you, Zach and Ellie, if you remember, but we used P for the letter for momentum. It doesn't really matter. At any rate, if V is pretty small, what we're going to find out is that, I think we did this last time, really this ends up being 1 minus 0, and P ends up being just M times V, which is kind of what we expect because that's what we learned it as anyway. But and this is review, you'll see why I'm reviewing it with you. If V is big, who remembers from yesterday? It was right at the end of the hour. What happens to the momentum as we get really close to the speed of light? So as V gets really close to C, so it'll be C squared over C squared. And what ends up happening to the number of the fraction from momentum? Thank you, Ellie. Good. So the bottom becomes small, so the fraction becomes huge. In fact, it becomes infinite. So we can write the little symbol for infinitely big. Infinitely big. Okay, thank you. Do I have Anne-Sophie or Teresa there? Be nice if I did, but we're going to go ahead and start anyway here. So, okay, the reason I'm bringing this up is because I want you to know where this really happens. In other words, we don't have spacecraft that can go this fast, but we do have some other stuff that can go this fast. And they found out that the things that go this fast obey Einstein's rules. Let's take a look. Especially if you've had other physics, you might know that if I shoot electrons, see, I'm going to write here EX example. Shoot electrons in a magnetic field. If I do that, what do the electrons do? Do you have a guess? So we're going to take here, I'm going to draw a little bit and you can tell me what they're going to do. Here's some electrons. We're going to shoot them at a high speed, close to C, between a magnetic field, so north and south. What do they do? What will they do? They're going this way. Yeah, good. Refract is what light does. Refract is a bending of light. When electrons or items bend, we have another word that starts with D. So shoot electrons in a magnetic field and they deflect. But it's the same idea, Ellie. They change directions just like light refracts, particles can deflect. So here's what they did. They put a little decoder out here. And I'm going to do this in two colors. What they expected was for the electrons to land here. They deflect, and they should land down here. That was predicted. Predicted. This is going to be like a plate here where they land, okay? And they could actually figure out on this thing where they hit. Good morning, Anne-Sophie. Super. Just need Teresa, and then we are complete. So what we're talking about, Anne-Sophie, is we're shooting electrons in a magnetic field, and they bend or deflect. And if we use Newton's ideas, the deflection should make them land right there, but they don't. Instead, they land here. So that's the actual landing spot. How about location? And of course, the question is, why? And I'm going to make a little whiteboard space, and you can maybe think about how to answer that. Do the best you can, Anne-Sophie. I hope we won't be interrupted with our Wi-Fi today, and I can send this to you. That's my goal. In case your Wi-Fi goes down. Okay, so yeah, so why do they land here instead, the green location instead of the blue location? Well, let's think of what happened. Okay, at the beginning of the hour, before Anne-Sophie joined us, we had, with Zach and Ellie, we described that if something's going really fast, close to C, it's got a lot more momentum. And let me see what Anne-Sophie wrote. Yine, and Sophie, I can't really answer that now. And I don't really know anyway. It's, I think, undecided, to be really honest. Okay, so back to our electrons. So here we go. They're going really fast. So the electrons are shot close to C. They're going really fast. So what that means is they got a lot of extra what? So they have more as predicted by Einstein. And the word is, thank you, Ellie, momentum. Big Mo. In other words, what I'm trying to say is Einstein was right again. Man, the guy must have been some kind of Einstein, huh? Okay. All right. You probably dealt with this. I don't know if I know you haven't driven a car, most of you yet, but if you've even driven something like bumper cars at the fair, you might have a feeling for this, or even a bicycle. If I have a really heavy load, it's hard to turn. If I'm in a smart car, the really tiny car, I can turn a corner pretty easily. But if I've got a really big, heavy limousine or Cadillac or something, I can't turn it that quick, and I end up over here. Well, that's kind of what Einstein said. Using his equation, we get a lot more momentum than Newton would have predicted. So Newton would have predicted here, but because of the extra momentum due to the fast speed, they actually land here. Actual location of the electrons. Yeah. Okay. Why did I spend a lot of time? Because, frankly, I want this to be something you understand it's real and it's not just sort of a theory. Turns out it's a theory that ends up being true when we test it. So Einstein's theories may not be perfect, but so far, with the different things that scientists have done, they test out pretty good. Okay, Ute. When scientists work with really small particles, as you may know, uh, electrons, protons, they're not the smallest things. There are other things like, yeah, exactly. And to be like a bus, right? They go further in the lane. Yeah, they got a lot of momentum. They're big. It's hard for them to turn tight for a number of reasons. But momentum is probably one. When scientists study things that make up electrons, protons, and neutrons, subatomic particles like muons and gluons and strange and quarks and all sorts of things. Those tests that they do with those little bitty things, they're moving also close to the speed of light. All of those scientists take into account Einstein's ideas to understand where they're landing when they're formed and when they're spun out and hit a spot where they can be absorbed and studied. Okay, so they use those all the time with that sort of subatomic particle work at places like CERN, CERN in Switzerland, or there's one in East Berlin called Bessie, which is a circular particle accelerator. There's one in Texas in the U.S. and so on. Smaller ones around the world. So, okay, new topic. Unless you guys got questions on momentum. All right, I'm going to make a little board space here. The new topic is one you might be waiting for. I don't know, but it's the equivalence of mass and energy. Okay, what did Einstein really say? I'm going to paraphrase his words in German, but translated in English. And he said mass is simply a form of congealed energy, which I like. Now, what sort of things congeal? Well, we use that word for like drops of hot fat on a stove. Okay, fat splatters out of your pan and it lands on the stove and it cools down and congeals and becomes a solid again. Okay, so I love that because it's so visual. Energy, if it congeals, becomes a mass of something. It goes from energy to being matter. So energy goes to matter. Matter as energy, we're going to call it energy of being. And another way to call that is in the business rest matter. Rest energy. So really, a way to look at it visually is here's some energy, and whatever we got that is energy required for a process makes mass. So energy required to make mass. Or, and our society uses more the opposite. And the opposite has more to do with this, okay? If mass disappears, so suddenly it's gone, poof, means energy is given off. So there's a cartoon way to think of it. So if I got a little poof and your mass disappears, you must have given off a lot of energy. Okay. So if you think about it, this rest mass is a kind of PE, or potential energy, like we learned about earlier in the class. Just like a rock on a hillside, that's got PE. So does an object at rest. So any object, as long as it's made of mass, So this one has energy because of its PE as we normally know it, has energy. And this has energy from its rest mass. Weird, huh? So any object could have, it's always got a rest mass if it's made of matter. And if it's up on a hill, it's got other PE as well. Okay, now the moment you've all been waiting for. What's the relationship between energy and mass? Is rest mass kind of like chem PE? Yes, Ellie, but only under specific circumstances, which we'll look at in just a couple minutes. So rest mass can be like chemical PE, and we'll see how that's done. Okay, so E equals mc squared. The most famous equation in the world. And now you know what it's all about, right? The E's for energy. And that's equal to mass. And the mass is, I'm pretty sure it's in kilograms. Let's see if I wrote that down here. You can tell how often I use that equation. Not real often. But I think it's kilograms because that's the standard in physics. Now, c squared is a really big number if you think about it. So it's 3.0 times 10 to the 8th squared. Holy smokes. So it's 9 times 10 to the 16th. And the energy is in. You guys remember what we had energy in? Energy was measured in what sort of a label? Thank you very much. You got it. Ellie's got it. Probably everybody's got it. So joules, exactly. Yeah. Not watts, but joules. Yeah. Okay. So energy in joules, and this is probably we're talking about rest energy here. Okay. So this E would be the, or sorry, this would be the rest mass here. Ready? That's this M. So the rest mass times c squared gives you this huge number of joules. Okay, so now let's see where we use this, and we'll get to Ellie's question about, is it a form of chem PE or not? And you'll see why my answer is not so easy, but it kind of is. Okay, so where do we use this? Let's find out. Turns out we use it with nuclear power. That's probably the most common place we use it, okay? So think of your Homer Simpson cooling tower, right? And your actual nuclear facility over here. And what happens is, I got it written somewhere down here. I think it's 1,000, but let's see. Yeah. You probably know we use watts now. That's, well, power plants. Yeah, I mean they make powers in watts. Okay, but really we're talking about the watts or joules per second. So it's the energy that the power plants are making. Okay, so we've got your nuclear stuff. Here's your nuclear fuel. and then it decays. And that decay, as you probably know, gives off energy. We're going to call these, like we do in chemistry, the products of decay. Now, here's the cool thing, okay? The products, gang, they don't look any different, but they're actually have lost about 1/1000th of their mass. If you take more physics, you'll learn about this. It's called a mass defect. And yeah, so we convert in a nuclear power plant mass to energy. So that's not a big difference. So if you look at the rods afterwards, they don't look any different. I'm sorry, but they really don't. But they've lost a certain amount of measurable mass. And using Einstein's equation, that's the amount that they actually lose. So you could guess that I can make, if I could convert fuel to energy perfectly, it would be a whole lot of energy. So let's talk about how much energy they make. A nuclear power plant makes about 1 megawatt per day. I think that's what it is. And remember, watts are joules per second, so that's megas 10 to the ninth, right? So I got 10 to the ninth joules per second. Well, joules, I guess we could say, per day. Okay. So that answer for your question, how much do they make? So that's a lot. Okay. But here's the really radical part. Okay. Let's say this sucker weighed a gram. Okay. If I could take a gram of this, oh, and I need some board space again. Hold on. If I could take something that weighs a gram, if one, not a kilogram, but just a gram, if 1 gram were totally converted to energy with Einstein's equation, then you'd end up equaling, ready for this? 90 thousand? No, 90 million joules. So the amount a nuclear power plant makes in a day, if I could change this cap to energy, pure energy, I could get 90 times that just instantly if I could do it. We can't do it, but if you could, it would be cool, and I'd have a really incredible source of energy from anything that's made of matter. Now, in addition to nuclear power plants, it's also done where nuclear fission takes place. We don't have any of these plants yet, although they're trying to build one. But it does happen where? Where does fusion happen all the time? Where does fusion happen all the time? If it wasn't happening, you would know it real quick, within 8 minutes. Not confusion, that would be in the US, but what about fusion? Where's fusion happening? Teresa, you're finally here. Okay, good. All right. So Teresa, I'll try and save this if I don't lose Wi-Fi connection so you can watch the earlier part later on. Okay, and I'll try and send it to you through the Google Classroom stream. Okay, so fusion happens in the sun. Thank you, Zach. And also in the sun, it is losing mass. So the sun, when it does this, also in fusion, 1/1000th of the mass undergoing fusion. So not the whole sun, but just the part that's doing the fusion. Okay. So 1/1000th of the mass undergoing fusion is converted. Now, the exciting part is they're trying to make fusion power plants, one in Europe and I think one in Japan, but I could be mistaken. And the deal is the fusion power would be really cool if they could do it because the only thing you get is helium, which doesn't hurt anybody, and your fuel is hydrogen, which is not radioactive. So this could be really cool. However, it takes 10,000 degrees Kelvin, which is higher than Celsius, and it's an incredible high temperature. So we can't do fusion easily on Earth. We end up putting more energy in than we get out. But this would be a great source, another way of converting mass to energy. Your questions, let me take a look. Yeah, the sun gets a little bit smaller every day, but the sun has so much fuel that we're not going to notice that getting smaller for a long time. And even if it all happened in one day, I'm not sure we'd notice if it lost one part out of 1,000 of its mass. But that amount of fusion is going to take billions of years for the sun to do. So it's not going to lose that mass anytime soon. But it's already lost a lot of it because it's been around for, they think, like 10 billion years. So it's got less mass now, Anne-Sophie, than it did when it started 10 billion years ago. We think we're kind of in the middle of the lifespan of about our sun. So you and I don't have to stay up worrying up late if our sun's going to keep going or not. It's looking pretty good. And thank you. That's the rule for all fusion events. So if I could do it, and I can do it, Zach, in a lab with a bunch of lasers, like focused, I could focus lasers on some special type of hydrogen, I can make it fuse, but I don't get enough energy out. The lasers cost so much energy at this point. But I can make that happen, and it's about 1/1000th of the mass of the hydrogen in the lab that is lost and is converted to energy. So yes, that's the same in every star and every sun, and every time we do this in a lab to do fusion as well. Good questions. Thanks everybody for your participation. It's kind of hard to teach in a part of my cellar. Okay, and now I'm going to erase this. Now we'll get to the heart of the question that I had earlier. Turns out, and Anne-Sophie and Ellie, this is good for you to know, turns out that even normal reactions lose a little mass if they're exothermic. So normal chemical reactions lose a little mass if they give off heat. And in chemistry, we call that exothermic. Now, it's not a lot. And this is why it took so long for scientists to figure this out. We're talking about like a billionth of a gram. So 1/1 1/1000th of the mass is lost. So not a lot, but a tiny, tiny bit. Let me give you an example of one that gives off energy, and some of the energy comes from this change due to changing the mass to energy. An awful lot of it comes, and Sophie and Ellie especially, from changes in the energy of the bonds. You end up with much lower energy bonds in the products. So most of the exothermicness, the giving off heat, has nothing to do with Einstein. Okay? So sorry to disappoint you. But let's do a regular example of this. Let's do something you're doing right now. You guys are burning glucose, C6H12O6, and I bet you had to memorize this, plus 6O2, and you're giving off carbon dioxide, 6 moles of that, and you're giving off water vapor, 6 moles of that, plus you're giving off some energy. So what I'm trying to say is 999,99999 out of a billion, all of that is from the changing in the bonds. So there's not a lot of this that's due to Einstein's ideas, but a little bit. 1/1000th of the mass is lost to make this energy right here. So I'll just write here, but most of the energy is not from changing mass to energy. Okay, so there's a disclaimer. So please don't go home and say, hey, I'm changing mass to energy in my body. You are, but only a tiny, tiny bit. But that is happening in you right now as well, which is kind of cool to think about. Okay, turns out I can also look at this in a way that is really weird, but they found out it's true. You ready? We're going to compare one column that says more mass and one column that says less mass. Turns out if you light up a light bulb, and I'm going to draw an old-fashioned one, and there's a little filament, right? That's what we call the inside of the light bulb. And you have a light bulb that's not lit up. So here it's cold. Turns out the one in the lit up, the one that's lit up weighs more. Isn't that wacky? So if I could weigh the two light bulbs and they're exactly the same, and I turn one of them on, because of the energy, the one that's on has more mass. Whoa, bizarre. It gets even weirder. Turns out, I'm going to draw a couple cups. If I've got hot tea, believe it or not, it weighs a tiny, tiny, tiny bit more than the same amount of cold tea. Whoa. Yeah, if you do the calculations, there's a little bit more mass if the tea is hot. Even if I have the same amount of molecules of tea in the next cup. Crazy. Last one, and this one is really weird, okay? I got to go over here with this last one. Well, I'll just go up to the top of the board. Okay. But this is the one I find the most fun. Think of an old-fashioned alarm clock. So here's your old-fashioned alarm clock. When I was a boy, we had one, and you had to wind it up. And it's got a spring inside that's wound up. So that it's running. Turns out that one has more energy, or more mass, pardon me, than if I got one that's not wound, so it's not running. So if my little spring is not wound up, spring not wound. Turns out even that change has less mass. Which is weird, because if you think about it, because a tightened spring, right? If I tighten a spring, I think we had that when we talked about types of energy. That's just like a type of PE, isn't it? It's potential energy if I tighten a spring. And yet even that causes a greater mass to be present. Isn't that weird? So in a sense, it is a bit, in sometimes, Ellie, like chemical PE in a really weird Einsteinian way. Okay, let me see if there's questions. Yeah. If there was no liquid in the two cups and one was hot and the other was cold, the hot one would still weigh more, even without the liquid. If it's hotter and it's the same amount of particles, it weighs more by a tiny, tiny amount, but it does weigh more. Weird. Again, we're talking like billionths of a amount of the mass. But still, hey, right? But still. Okay, let's go back and work a little bit more with equations. Basically, the cool thing about Einstein is he found that energy and mass are the same thing. Energy and mass are the same darn thing. Okay, let's talk about relativistic kinetic energy. We all remember, right? Kinetic energy, energy of motion. Yep. I'll wait for your question, Ellie. Ellie's question, if you're using energy, you have more mass. Let's make it that you're given energy, Ellie. So let's make it not that you're using it, but let's say that you're a light bulb and you get electrified. Then, because of the energy in you, you actually will have more mass than the next light bulb over that's identical to you that has not been lit up. That's kind of what I mean. Or let's take the other part of your question. Yeah, you had another part I want to answer too. I thought. Yeah, so you got to use, somehow I've got to get energy to make that mass. And so if I've got extra energy given to me, I've got extra mass. And the weird thing about the clocks that I just erased is, it's like I haven't even zapped them with electricity, but just by winding one and setting it there, just because of that, there's a fraction more of energy, somehow more of mass, than one that's equivalent that's not wound. Yeah. Again, I don't know how they've proven that or looked at that, but apparently that's the case. Really weird. That one throws me every year. Okay, I'm going to skip this one because I really want. Okay, let's give you first two equations. Okay, so let's give you an equation for the E. So it's the total energy of an object. Let me make sure this makes sense. Total energy minus the rest energy. And it's going to use that factor we had before. So it's mc squared divided by, and again, it's got to be going pretty quick, square root of, as per usual, 1 minus v squared over c squared. Okay, I got to read my notes on this. So if v equals 0, then it's just the bottom falls out, as you could probably figure out. It's just whatever over 1, so then it's E equals mc squared. But if E's going fast, then I've got more energy. Okay, so on to kinetic energy. So kinetic energy is equal to the total energy of the object minus the rest energy. It's not resting anymore, it's in motion. So apparently that means we got to subtract it. It's a little strange even for me, but I'm going to give you the equation. So the equation is mc squared divided by square root of 1 minus v squared over c squared. So same as up above. All of that minus, minus mc squared. Now, it looks troubling, but if we throw some numbers in, you'll find out it does make sense. Okay, if I'm not moving, I got how much kinetic energy? I know you're writing like mad, but see if somebody can answer. If I'm not moving, I got how much kinetic energy? Thank you. I got none. Okay, so if I put in a velocity of 0, this better come out to 0. Okay, if v equals 0 meters per second, let's do that mentally. So I'd have 0 squared over c squared, well, that would just be 0. 1 minus 0 is 0. Square root of that is 1. But that's just mc squared over 1 would just be mc squared. But then mc squared minus mc squared is 0. Then it does work. If the velocity is 0 meters per second, my ke, not ko, that would be in a knockout fight, my ke would be 0 joules, or none. Now, if I got a big number here, a velocity that's close to c, then it gets closer to 1. And then I get that same thing as in the other fraction. I got this thing becomes really, really, really small. So I get a big number divided by a super small number, which means it's an enormous number minus this, which ends up being less enormous by comparison. So if, I'll write it over here, if V is close to C, and we can put in some numbers when we do some problems. Good, everybody answered the last one. Thank you. Yeah. So if V is close to C here, then KE becomes infinite. I'll draw a little infinity symbol, or infinitely big. Well, you might say, so what? Well, here's the problem. Now let's talk about human space travel. I want to travel at a really high rate of speed because otherwise it's going to take me years to get to another planet, another sun, whatever, another star. If I get really close to C and my kinetic energy becomes infinite, how much fuel do I have to have? In other words, the fuel needed for space travel close to the speed of light would be how much? Everybody, exactly right. Anne Sophie, Zach, everybody, good. So would be infinite. That is a major bummer, as we said when I was your age. It's too bad because space travel at sea, or if you remember the Star Trek series at Warp 1 or Warp 2 or Warp 3, it's really looking not real possible. Not only can I not go faster than C, I can't get very close either because I'd need so much fuel to do it because my KE becomes infinite. And because of that, I need an awful lot of fuel. So we got some problems about trying to get to the next star anytime quickly. Remember, if I could go the speed of light, the next star is like 4.5 years away. We say 4.5 light years. So even if I could go see, it's still 4.5 years to get there. Space is really, really big and it's full of a lot of nothing. Most things out there are nothing. It's amazing. Okay, I'll stop. I'll stop myself. How are we doing? We're still doing okay. Good. We can maybe finish up today. Well, so what is all this going on? All right. So yeah, an object has energy even at rest. An object speed as an object speed approaches c, its momentum and energy approach infinity. So no object can go the speed of light. That's kind of what I'm trying to say. No object can go to c from what we know now. Again, why? Infinite Ke and momentum make fuel a big problem. As it turns out, there's other problems too. Yeah, about going the speed of light, but that's enough to make it a logistical problem for space travel. Okay. See if you got any other questions before we change gears a little bit. We're going to compare Einstein with somebody else in just a moment. Let's see. Could there be an object that has an unlimited amount of fuel? Now that is a great question, Anne Sophie. And if so, what would that fuel be? And what would that object be made out of? How would that carry the fuel? What would all of this look like? I'm not saying it's impossible, but it's something no one's really comprehended yet how to do. Could it be possible to create in the future? And Sophie, do it. I hope you can. That'd be great. So far, it's not looking very good, but hey, oh, where'd my markers go? There's one. Okay. All right. I want to take a little walk backwards to a guy that we studied in chem, and you might know his name, Niels Bohr. Niels Bohr did a lot of atomic model work back around 1900, 1910, 1920. He was one of the fathers of this idea that electrons are in orbitals, and refining that are in areas of probability of finding them around the nucleus. Okay, so Niels Bohr was a pretty good guy who knew about theories, and he said this about theories. Okay, you'll see why I'm bringing this up. He said there has to be a correspondence principle. So what the heck is a correspondence principle? Well, it says that a new theory must agree with an old theory if the old one still works. He didn't say it in this, so I won't put it in quotes, but exactly. So anyway, the new theory we're going to look at are Einstein's theories, relatively new. And the theories at the time were several hundreds of years old, and that was our guy whose name started with M. So I want to compare two worlds. We're going to do three relativistic equations. Relativistic equation. And then we're going to put in zero and zero for the velocity. Let's do the first one, and then we'll make a third column here. So save a little room out here. Okay, let's do one for the time dilation. And we'll do some problems with these maybe next week. For time dilation, it looked like this. The time was the rest time, T0, divided by this correction, square root of 1 minus b squared over c squared. And if I put in 0 in for v, then I get what? I get t equals the original time, or time in a rest frame of reference, divided by 1 minus, well, if I put in 0, then that just becomes 1 minus 0. Or in other words, t equals t. And this would be what we would call the original agreement, the original theory from the guy we call Newton. So essentially, this is a Newton equation. or Newtonian equation. And Newton would say time is time. So T0 to Newton would be what he would call regular time. So if we're in a Newton world and we're going a velocity that's pretty low compared to the speed of light, then essentially, even if it's going as fast as a jet plane, compared to the speed of light, that's nothing. So still, time becomes the same, unless we measure really carefully, like they did with the jet planes in the 1970s. So generally, Newton would say, hey, time is time. There's not any real difference if you're going relatively slow compared to c. Let's do a couple more. How's our time? Our time is over. Let's do the last couple of them next time. But we've got through the first one. It'll just take 5 minutes of our next hour. What I'm going to send you to do, though, I'm going to send you a worksheet, and we're not going to meet tomorrow. The worksheet I'll have due next Tuesday, so you got time. I think the worksheet will take you guys 15 minutes at the most. I don't want it to be hard. And I'm going to give you a problem with length contraction, and you're going to try using the length contraction equation that you should all have. If you weren't here or whatever, look it up on the internet. And then a couple other kind of fun questions to think about, okay? I'm going to send that to you through Google Classroom. And again, let's have it due next Tuesday when I see you. Okay, so you got a little time to work on it. Thanks, everybody, for meeting. Let me read the last comment. Why does this show up all the time? This square root of 1 minus v squared over c squared n sub phi, it's kind of like the correction factor because of Einstein's ideas. So we'll see that in all three equations that we do. We'll do the two other ones next Tuesday. Can we email you with questions? Absolutely. That would be just fine. Okay, how about the worksheet? The worksheet, yeah, you can email me about questions on the worksheet as well, but it's pretty short. So you may not have a lot. Good. Thanks, everybody. Have a good, safe rest of your day. We'll see you next Tuesday. Bye.